Hello everyone, Steve Eggins here. This week's topic in Blue Planet is Introduction to Cycles and Residence Time. The goal for the week is to develop tools for understanding cycles using the concepts of reservoirs, fluxes and residence time. Why should we try and understand cycles? Well, if you're planning to live in the 21st century, you should probably understand how carbon and hydrological cycle changes arising from fossil fuel burning will influence and impact the Earth system. You could rely on Hollywood or vested interests for this understanding, or you could develop your own based on evidence and knowledge of how the carbon and hydrological cycles work. So our learning objectives in this first lecture really revolve around cycles and residence time. We want to understand the concepts of reservoirs, stocks and fluxes. Fluxes are the exchanges between the reservoirs. We also want to understand what is meant by steady state and how we know when a cycle or part of a cycle is in steady state. There are a number of other learning objectives that we'll get to later on in this lecture and also later on during the week. So let's think about some basic concepts and terminologies with cycles. So with Luigi, you've spent a little bit of time learning about the hydrological cycle. So global scale cycles like the hydrological cycle or the carbon cycle can be understood and modelled by dividing the Earth into reservoirs, where substances like water or carbon, or alternatively, you can do the same thing with energy, are stored. And then you can quantify the fluxes, the rates of flow of those substances or energy between the reservoirs. In the case of the hydrological cycle, we can identify some large reservoirs of water in the Earth system. These include things like ice sheets, the oceans, lakes and streams, the atmosphere, and groundwater. So before we move on to take a look at the hydrological cycle, let's get some basic concepts and terminology. So a reservoir, like the ocean, contains a pool or stock, an amount of stored matter. In the case of the ocean, that's water or energy. A flux is the rate of exchange of matter or substance from one reservoir to another. So that would be, for example, the amount of water that gets evaporated from the ocean to the atmosphere in a certain amount of time. Fluxes have units of amount divided by time. Those units are like litres per second, tonnes per year, and that sort of thing. So here we have a reservoir, like the ocean, and then we have an input flux. So the ocean has water in it, and there will be an input flux into the ocean, and there will be an output flux from the ocean of water. So water coming in, water going out. Okay, so homing in on the hydrological cycle. So the cycling of water through the hydrological cycle is constrained by mass conservation. We're unable to, the water is conserved across the whole cycle. And so we're neither creating or destroying water, we're just moving it around. So if we move some water from a reservoir, it has to go somewhere else in the system. So in this diagram here, in these boxes, in the white boxes with the black numbers, we have the volumes of water in thousands of cubic kilometres. And so if you have a look at these boxes, you can see that the ocean here has 1,338,000 cubic kilometres of water in it. The amount of water in the atmosphere over the sea is 10,000 cubic kilometres of water. The amount of water in glaciers and snow and ice sheets is 24,000 cubic kilometres of water. These are very big numbers. So the arrows on the diagram, so here's an arrow here. In this case, these arrows represent the fluxes between the reservoirs. In this case here, we have the flux between the atmosphere over the ocean into the ocean. So this is precipitation over the ocean. So this flux has to have units of amount divided by time. And this flux here is 391,000 cubic kilometres per year. So those units you can see down here. And if you look around the diagram, you can see all the fluxes between all the different reservoirs. So as I was saying before, with the hydrological cycle, the major reservoirs include the ocean, with this very large number, over a million times 1,000 cubic kilometres of water, or over 1 billion cubic kilometres of water in the ocean. It's then followed by the glaciers and snow, which include, this number here includes the ice sheets. Then we have groundwater down here. This is the water that's buried at depth below the soils in rocks. And there's a very large amount there as well. That's 23,400 times 10 to the 3 cubic kilometres. Permafrost, 300,000 cubic kilometres. Lakes, 175,000 cubic kilometres. And then we have some smaller reservoirs like wetlands, the amount of water that's in rivers, and that sort of thing. So if we total them all up, we come to this very large amount of water in the total system, which is over 1 billion cubic kilometres of water. That's a lot of water. So let's consider the atmosphere now. So the atmosphere on this diagram actually contains two parts, and it's divided up here so that we have the atmosphere over the ocean and we have the atmosphere over the land. So you can see that there's 10,000 cubic kilometres of water in the atmosphere over the ocean, and there's 3,000 cubic kilometres of water as water vapour in the atmosphere over the land. So that's the total reservoir size of the atmosphere is 13,000 cubic kilometres of liquid water. Let's now have a look at the input fluxes to the atmosphere. So here they are here. There's evaporation from the ocean into the atmosphere over the ocean. And you can see each year there's 436.5 thousand cubic kilometres of water evaporated annually from the ocean into the atmosphere over the ocean. The total, we also have water evaporation over land, so that's here under total terrestrial evapotranspiration, and that number is 65,500 cubic kilometres of water annually into the atmosphere over the land. So when we total those two up, we have a total input to the atmosphere of 502,000 cubic kilometres of water a year. That's a lot of evaporation. If we now go and look at output fluxes from the atmosphere, then we have total precipitation over the ocean, from the atmosphere over the ocean into the ocean, and that's 391,000 cubic kilometres per year. And from the atmosphere over land onto land, we have 111,000 cubic kilometres per year. And you'll notice that that number adds up to exactly the same number as the input fluxes to the atmosphere. So effectively, it's a bit like what goes up must come down. So the amount of water that gets evaporated into the atmosphere each year also precipitates out of the atmosphere each year. So these numbers are both the same, which shouldn't really come as a surprise. So the inputs to the atmosphere equal the outputs from the atmosphere. And we can say that the H2, the water fluxes into and out of the atmosphere, are balanced. Let's now move on and have a look at the ocean. So in the case of the ocean, the reservoir size, as we noted before, was over 1 billion cubic kilometres of water. The input fluxes to the ocean are, looking closely at this diagram again, we have, here's the biggest input flux here, which is the precipitation over the ocean from the atmosphere overlying the ocean. There is another input flux to the ocean here, and you'll find it here, and that is the riverine input to the ocean. So the water that flows down the rivers off the land into the ocean is another major flux into the ocean. And they're noted there. And when we tally those up, we come up with a number of 436,500 cubic kilometres of water each year flows into the ocean, precipitates or flows into the ocean. Similarly, if we look at the output fluxes from the ocean, there is one major output flux, and that is the evaporation from the ocean into the atmosphere overlying the ocean. And you'll notice the number there, 436,500 cubic kilometres equals the input fluxes to the ocean. An interesting little side note here is that the net water vapour transport flux from the atmosphere overlying the ocean to the atmosphere overlying the land is 45,500 cubic kilometres per year. And not surprisingly, that actually is balanced by the riverine flow back into the ocean from the land. And so again, we have the balance of the input fluxes into the ocean equal the output fluxes from the ocean. So let's have a look at the concept of steady state. If the input and output fluxes of a substance or energy within a system to and from a reservoir are equal or balanced, then the amount of the substance or energy in a reservoir will not change with time. So if the amount going into a reservoir equals the amount coming out, then the amount in the reservoir will stay the same. It's a bit like your bank account balance. If you put $100 in every week, you've got $1,000 in there, and then you spend $100 every week, you'll still have $1,000 in there after each week. Your account is in steady state. Good place to be. So, however, if the input fluxes are greater than the output fluxes, the amount in a reservoir will increase with time. If the input fluxes are less than the output fluxes, the amount in a reservoir will decrease with time. So here's a diagram of sea level change over the last 100+ years. So what we've seen in the big hydrological cycle model is that the ocean, the inputs into the ocean are roughly equivalent to the outputs from the ocean each year. And on that basis, we were expecting the ocean to be in steady state. But is that really true given a diagram like this? So I would suggest you pause and pause the video and have a think about what might be going on here. And is that really true? Is the ocean really in steady state given data like this? And what might be the reasons for this sea level change? So just have a think about that for a minute and then come back. Okay, so there are a number of reasons why this is actually happening, this sea level rise, when we think about the hydrological cycle. So part of it is actually not due to an imbalance in the input and output fluxes, and that is part of this sea level rise is just simply due to the thermal expansion of the oceans with global warming. But there are some other contributing reservoirs to the ocean. So we have melting of the ice sheets, which are delivering more water to the oceans. And we also have removal of groundwater on the continents. So that gets pumped onto irrigation fields and more of that water ends up flying into rivers and then into the ocean. So there are a number of reasons why the water's actually going up. And then there's another thing that's actually damping the rise, and that is the building of dams over land, which are storing some of the water that would otherwise flow into the ocean or otherwise be in the ocean, is being stored on land in dams. Okay, so we're going to take this little exercise of thinking about reservoir sizes and fluxes in a slightly different way. So you could do this with your bank account, for example, but we're going to do it with Australia's population. So on Saturday evening, at around 7 p.m. Canberra time, the population of Australia is projected by the Australian Bureau of Statistics to be 25,682,602 people. And so here's the plot over here of the increase in population of Australia from here, well below 5 million people in 1900. And so over the last 120 years, we've added almost 20 million people, and you can see that the rise is steepening. And that particular, you can even see that over the last 20 years or so, that it's even steepened further. So let's think about this in terms of fluxes in and out of this reservoir of people, i.e. the number of people in Australia's population. So the actual number is based on an estimate of the resident population at the 30th of September 2019, which I think was the last date of this last census date in Australia. And it assumes growth of the following: 1 birth every 1 minute and 44 seconds. So that's a birth rate or a flux rate of people of 0.00962 births per second. So that's an input flux into Australia's population. At the same time, we have a death rate, or 1 death every 3 minutes and 11 seconds. So if you work that out in terms of a flux, that is 0.00524 deaths per second. So that's an output flux. We also have 1 person migrating to live in Australia every minute, and that is around about 0.01666 births per second on average. And we have, on average, also 1 Australian resident leaving to live overseas every 1 minute and 44 seconds. And you'll see that I've got the units wrong there. That should be, these should be people per second. So here we have 0.00962 people per second migrating out of Australia. So if we add up these input fluxes and output fluxes, we can work out what the net rate of increase of population is in Australia as a flux or a net flux. So when we do that, this is made somewhat simple because this input flux equals that output flux, so they cancel each other, and then we have the difference is is between the rate of migration into Australia minus the number of deaths, or the death rate in Australia. And we end up with 0.01142 persons per second, or about 1 person every 1 minute and 28 seconds. So this is where we normally have a bit of fun in a lecture situation, because we ask you, the students, and you generally do this in groups, how you would go about returning the Australian population to steady state. So obviously there are a number of levers and ways that you can do this. And I'll just let you think about what they are. So again, pause and have a think about what you might be able to do to bring the Australian population to a steady state situation where the input fluxes equal the output fluxes. So some of the suggestions are that you can obviously up the birth rate, and that's what a famous Australian treasurer once did about 20 years ago. They offered couples in Australia $5,000 for every child that they had. So that was a mechanism that they used. Obviously, you can up the migration. We could. Oops, I've actually done this wrong. If we have to balance this, obviously we either have to decrease the input fluxes or increase the output fluxes. So if we're going to increase the input fluxes, decrease the input fluxes, then we need to reduce the birth rate. Or we need to decrease the number of people migrating to Australia. Alternatively, we could increase the death rate. So we could go around shooting people, for example, or we might encourage people to move overseas. Obviously, both ridiculous suggestions, but they're the sort of things that people come up with. So an interesting thing at the current time is that you will notice that both the number of people migrating into Australia and the number of people leaving Australia will almost have gone back to zero during the COVID-19 pandemic, and that's likely to be the situation for a whole year. But as you see from here, the population will likely continue to increase because the birth rate exceeds the death rate. Another interesting thing about the COVID-19 pandemic is if you actually work out the additional death rate due to COVID-19, we've had about 100 persons die over about 50 days, and that's only about 0.00002 persons per second. So that has a very small impact on the overall net rate of population increase in Australia.